Okay, so the delay lock loop circuit that we have seen in the class so far, which involves a reference signal getting delayed. And then we compare the delayed version of the reference with the next edge of the reference using a PFD plus a charge pump followed by a capacitor, so that we can generate a control voltage VC, and we use this to control the VCDL. Now, such a delay lock loop is what is called as a type 1 DLL. Okay, so if there is a type 1 DLL, you can expect that there would be a type 2 DLL, and this is what you saw during your midsem exam. So a type 2 DLL basically has two inputs. One could be a reference, the other is some input signal. And this input signal is what is now getting delayed through a VCDL. So both of these are clock and they have the same frequency. And then we compare the edges of this in, the delayed version of the in, with the reference, again, using PFD plus charge pump plus the capacitor. So this generates a control node voltage, and that is used to control the VCDL. So this is my out waveform. So under steady state, what do you expect to see between out and reference? Locked in the sense that their rising edges would occur at exactly the same time, right? So that would mean that the delay of the VCDL, can I say that this is equal to TRF? No, it need not be TRF. The actual delay of the VCDL will depend upon what the initial phase difference between reference and in is. Depending on that phase difference, this will add additional delay such that the in and the out and the reference edges are now in sync. Okay, so this delay you can expect it to be anywhere between 0 to TRF if there is no harmonic locking involved. But as such, in this circuit, there is no issue with any harmonic locking, right? This circuit is basically designed such that the out and the reference edges are occurring exactly at the same time. Okay, so let us quickly sketch out its small signal model. So we are looking at its small signal phase domain model. So the PFD is going to calculate the error between phi ref of S and phi out of S. And then it goes through PFD, charge pump, and the capacitor. So this is my phi error of S. So the error is calculated. It sees a gain of ICP by 2 pi into 1 by SC. This gives us VC of S. This gets multiplied with KDL in radians. And then phi in of S, and this gets added together to give us the phi out of S. So this is the small signal phase domain model. Okay. Now, if I have to calculate the loop gain, so first we have to identify the loop, and the loop is basically here, right? So now to calculate the loop gain, what should I do to the input sources? I have to de-energize them, right? So they are made to be 0. So this goes to 0. This also goes to 0. Then I break the loop. and I inject a test signal. And I go around the loop and see what comes out at the other end. So this calculation is pretty straightforward. So this is phi test of S. It goes through, so there is a negative sign here. So minus phi test of S into ICP by 2 pi C KDLR into 1 by S. This is equal to phi out of S. So minus of the loop gain function will be equal to minus of phi out of S by phi test of S. And what is this equal to? ICP KDLR by 2 pi C into 1 by S. Okay. So then a quick calculation that we can do is to see the unity loop gain frequency, that is omega u. So to get this, I basically have to take LG of j omega u and equate this to 1. And what does this give us? So this is ICP KDLR by 2 pi C. So up to this, the calculations look very similar, right? And what comments can you make about the stability? Yeah, this is unconditionally stable, right? Because there is only one pole. Therefore, the phase margin is always going to be 90 degrees. Okay. So now let us calculate what is phi out of S by phi ref of S. So let me simplify this loop. I can represent this as omega u by S. Okay, so now to calculate phi out of S by phi ref of S, what is the first step? Phi in of S should be 0. Why? But why is that valid? Superposition. So this model is now linear, right? Therefore, if I have two inputs and I want to calculate the transfer function from one input to the output, I de-energize one of the inputs so that I can apply superposition. So in this case, I make my phi in of S to be 0. Therefore, again, minus sign here. Phi ref of S minus phi out of S into omega u by S will be equal to phi out of S. Therefore, phi ref of S into omega u by S is equal to phi out of S into 1 plus omega u by S. Therefore, phi out of S by phi ref of S is given by 1 by 1 plus S by omega u. Okay, so now if I plot the magnitude of phi out by phi ref versus omega, this also in log scale, what do I get? The low pass transfer function, where this happens at omega u. Okay, now why does this make sense? Does it make sense? Is there an intuitive reasoning behind the transfer function from phi ref to phi out being a low pass transfer function? At high frequency? Basically, this gain is very, very small, equal to 0. Correct.
fire was directly getting into the fire. So at that time, it was directly affecting the 41, 30.
Okay.
Now it's not related to the from output to fire is not related.
So is that clear? So at very low frequencies, this path has a very large gain, which means it will try to make the phi error to be equal to 0. So that would mean phi ref of S and phi out of S should be equal. Now, for very high frequencies, this path has 0 gain, right? Which means that the loop is not able to account, not able to push any additional phase here, even if it is able to detect a phi error. Therefore, phi error need not be equal to 0. Therefore, phi ref and phi out need not match. Therefore, phi ref will have a low pass transfer function to the output. Okay. So given this reasoning, what guesses can you make about the transfer function from phi in to phi out? All pass. So why don't we calculate this? So you have to calculate phi out of S by phi in of S. Please try. High pass. Okay. So what expression do you get? So others, please calculate. Now to calculate this, we first have to make phi ref of S to be equal to 0. Then phi out of S will be equal to phi in of S minus phi out of S into omega u by S. Phi out of S into 1 plus omega u by S is equal to phi in of S. Therefore, phi out by phi in is equal to, so if you solve this, you'll get S by omega u divided by 1 plus S by omega u. Now, if I look at the transfer function, what do I get? So assume everything is in log scale. So what is the shape? This is high pass filtering. So does this make sense? Why?
We have a perfect ideal negative feedback from and I have to that feedback gain becomes
0.
Negative.
Right. So is that clear to everyone? Is it clear? Okay. Okay. So now there is a small correction in the previous lecture. So in lecture 12, when we derive, we missed out on a Z in the denominator. There is an additional Z. So this doesn't affect the stability because this is at the position Z equal to 0. So it is well within the unit circle. So it doesn't affect any of the calculations we did, but we missed out on the Z factor. Okay, so now let us quickly look at some of the applications of the delay lock loop. So one major application we saw in the last class itself, this is related to TDC implementation. And what we saw was a flash TDC. Now, flash TDC is just one type of TDC that you can implement based on the delay stabilization using a delay lock loop. So there is another TDC, which is called as a Vernier TDC. Right? And this is basically similar to the Vernier scale experiment that you have done previously, right? So the idea is that I want to get a resolution, and this resolution happens to be smaller than any delay that I can realize reliably on chip. It's smaller than an inverter or a buffer delay. So similar to the question again asked in the mid-semester. So what we do is, instead of relying on a single buffer delay, we make sure that we have two buffers, and the difference between these two buffer delays is equal to the resolution, correct? So in fact, what we'll have is, we'll have some, let's say we have a stop signal and a start signal. In the flash TDC architecture, we had a setup something like this. Right? Where this delay was basically the resolution. Now, instead of a setup like this, we will now introduce delays in the stop path as well. And let's say this had a delay of T2, this had a delay of T1. So this is completely T2, this is T1. And the resolution would be T2 minus T1. So based on the TDCs that you have seen so far, should T2 be greater than or less than T1? It has to be greater than T1, right? And the T resolution will be given by T2 minus T1. Okay. Now to achieve this T2 and T1 across PVT, I can use a delay lock loop. So the brute force method is to realize T2 using one DLL, let's say DLL1, then use another DLL. So maybe we should use naming convention like this, and use another DLL to realize the next delay. Okay. So if I were to follow this brute force method and I had a 1 nanosecond clock, then one option in front of me, so 1 nanosecond is basically T clock for us. Now the resolution I can realize would be some T clock by M, right? So I could have T clock by N1 giving me T1, and then T clock by N2 giving me T2. Okay. So in this case, one possible solution is to use N1 is equal to 5 and N2 is equal to 4. So this will give you 250 picoseconds, and this will give you 200 picoseconds. There could be multiple answers. This is a design problem, so multiple answers are expected, but this is one possible solution. Okay, so the answer expected was something like this. So you have your reference signal, which has a period of 1 nanosecond. Then you use PFD, charge pump capacitor, generate a VC1 voltage, and this VC1, you feed it to a VCDL consisting of 5 VCDUs. So the delay of each VCDU will now be equal to 200 picosecond. Okay. So let me call this as VCDU1. Now in this circuit, these are VCDU1 and T1 is equal to 200 picosecond. Now for T2, you use another DLL where there are 4 VCDUs, and then you stabilize it using PFD plus charge pump plus capacitor. So this gives you VC2, and the same VC2 has to be fed to all of these. So if this is VCDU2, this will be VCDU2, And you have to show VC1 being connected to all of these and VC2 being connected to these. Okay. So how many stages should I have like this? So if I call this as one stage, how many stages should I have like this to achieve the range of 500 picosecond? I should have 10 stages. So you should have O1, O2, O3, etc. up to 10. Simply put dots and show the last stage here. That would have been sufficient. So this is one way to realize a Vernier TDC. Okay. Now, let's say I want to retain this structure as it is. Don't worry about the exact delay numbers. I want to retain this structure, but I want to use a single loop to stabilize both of these. Basically, I want to use a single loop to get the required resolution. Is there a way to do this? Take a minute and you can think and let me know. Yes. So I basically have a reference signal. The same reference signal is going through two delay chains. One delay chain is not in any feedback. So you get whatever delay this chain is giving you under a given PVT condition, right? Let me call its output as out1. The other delay chain is in a feedback loop, right? So the delay of this chain is going to be tightly controlled. And we have out1 and out2 being compared to calculate the error and then control this delay chain. So let us consider a reference signal. Right? So let's say there is some out1. Now let's assume that there are n elements in this delay chain. So if the delay of each buffer is T1, this delay is simply going to be n times T1, where T1 is not stabilized. All right. Now out2, again, if there are n elements and if that each has a delay of T2, this will be at n T2, and this is going to be some delay like this. Now the PFD is comparing these two edges. Correct? PFD is going to compare the edges of the out1 and out2. What would be the locking condition? PFD has control only over output. Correct? So if I think of the regular operation of a delay lock loop, then we are going to lock this edge to the next edge. Correct? Therefore, the total delay from the reference edge to the output is simply going to be, what is this much? What is this delay? This will be equal to NT1 plus 1 Okay. So now let me calculate what is NT2 minus NT1. What would this value be? So now the NT2 is what is providing you so much delay. Right? So what is this value? This will be equal to NT1 plus T clock minus NT1. Okay. Is that clear? Now we will have this edge appearing here. Once it is correctly locked, right? Therefore, this will be equal to T clock. Therefore, T2 minus T1 will be equal to T clock by N. Okay, so T1 is not controlled, but just by controlling T2, we are able to achieve T2 minus T1 to be equal to T clock by N. Okay, so can you tell me what should be the value of N if I wanted a resolution of 50 picosecond and if reference was equal to 1 nanosecond? N should be equal to 20. Okay. Is this clear? Okay. So now just for completeness, let me give you an associated question. Let's say I have some input going through a buffer. And this is my output. Okay. I have a resistor chain connected like this. And let me call this as V1, V2, and V3. Okay, you can do this as a homework, but plot V1, V2, and V3 qualitatively, assuming you have input and output waveform like this. And you have some output appearing. Okay, so a small delay is there between these two edges. And how would the waveforms V1, V2, and V3 look like? You have to plot. And then you can read up on what is called as phase interpolation. Okay. So another application of delay lock loop is deskewing of the clock. Let's say I have a digital circuit. Right? This has a clock signal. And let's say this has multiple data signals. So if you have a clock and data signal going into a digital circuit, we need to know the exact phase relationship between clock and the data, right? We would generally expect, so for example, if this is the clock, we would expect the data to change either at the rising edges or maybe the data is changing at the falling edges. And we need to know this exact relationship so that we can check if the setup and hold times are met within the digital circuit. Okay. Now this clock signal is going to multiple nodes within the circuit. That means it is going to see a larger load capacitance, right? Therefore, to drive this large load capacitance, we would generally have multiple buffers driving this. Right? So if I call this as the clock one signal is going to be a delayed version of the clock. Right? And if this had a delay of TD, so this is TD, but this TD is now a function of PVT, which means at different process voltage and temperature conditions, the phase relationship between clock and data is now not clearly known. Okay, and this is a problem because it could lead to failures, timing errors within your logical circuit. Okay, so how can we correct this? So a very good solution would have been to make TD equal to 0 at all corners. Now that is not possible, right? Anytime you introduce a buffer, it is going to give you some delay. So what else can we do? If I can't make TD equal to 0, what is the next best solution? Right. If I can provide, so you're saying provide extra delay in the data, right? So that is one solution, which means I will have to add similar buffers everywhere. Is there a better solution? Correct. So now if I can delay the clock one edges such that it goes and logs to the next edge, then also the phase relationship between clock and data will be maintained, right? So to do that, we could add a variable delay line here and then simply tune this variable delay line such that the overall delay is still equal to T clock. Okay, so to do this, so we have our clock. This first goes through a variable delay line. Then it goes through the clock buffers. And this is the clock one, which is going to the circuit. And we compare these two using PFT plus charge pump plus the capacitor and control this VCDL such that this overall delay is now equal to 1 clock period. Again, this is one of those applications where harmonic clocking doesn't matter because we are interested in only aligning the edges of the clock. Is this clear? So last time when I taught this, a student had asked a very interesting question. So if the VCDL is anyways consisted of buffers, why do I need this separately? Why can't I combine both and make a bigger VCDL chip? So any comments on that? Okay. If it was possible to absorb it, should I have absorbed it or? Not really, right? VCDL is needed so that the total delay needs to be 1 clock period, right? So whether the buffers are part of the VCDL or not, I need a VCDL to tune this to 1 clock period. So these buffers are maybe we will be getting some extra for okay. Same job can be, same result can be achieved. We can have this. Okay, so again, it's not a very clean answer here. So again, like Pankaj mentioned, maybe it's possible that these buffers are not accessible to us. It's designed by a different designer, and he just gives us access to this point. And we are designing the DLL. So we access this point and then control the delay of the VCDL. That is one possibility. Now, another possibility is these buffers are designed for a different purpose. They are designed for driving a large load, right? And this VCDL is designed to provide a variable delay. Now, if I try to combine these two requirements, it might complicate the system unnecessarily. So I make that into two components. One is designed solely to drive a large load. The other one is designed to provide a variable delay. So this can be a low power VCDL, small size inverters, just to provide a delay. And this is taking care of driving a large load. Now, in some application, if you find that it is easier to combine both of them, then you are free to do that as well. This is okay? To drive the using the VCD, yeah. But I thought you meant that it can be combined. Right. Okay. So with this, we sort of have covered all the portions related to the delay lock loop. So your project one statement will be uploaded in a day or two, and that is related to a DLL design. So you'll be doing this in LT Spice. Specifications will be given to you. And you can decide how to choose the number of VCDs in the VCDL, how to size the transistors, PFT, how to do PFT capacitor design, etc. But you have to clearly show the design methodology that you have followed. That's okay. So next we move on to noise signals. So we are finally interested in learning about phase noise, jitter, etc. But to be able to understand these quantities properly, we first have to understand some basics related to noise. Okay. So what is the one feature about noise that we are sure about? It's a random signal, right? What does that mean? Yeah, you can't predict what the next few values of noise are going to be. If I pick any time t, we have no clue what the value of noise at that instant is going to be, right? So we still have to deal with noise in our circuits. We still have to check if the circuit is behaving as we expect, even in the presence of all these random signals. Therefore, we have to rely on statistical models. Now, we can do this either in time domain or we can do this in frequency domain. So in time domain, we look at its PDF, probability density function. In frequency domain, what do we look at? So we look at what is called as the power spectral density. Okay. So let's say I have some noise signal, xn of t. This is going to be some random signal, right? Now I can look at its amplitude and then plot a histogram based on its amplitude. So what I'm doing is, on the x-axis is the amplitude, and on y-axis, I'm looking at the probability with which. Now, this noise is appearing due to multiple random events occurring within the device. And these random events are generally independent. Therefore, if you look at its amplitude distribution, you'll see that it has a Gaussian curve. And once you have a Gaussian curve, you immediately look at its mean and sigma. And sigma is a very useful quantity because it tells us the probability with which a particular amplitude can occur, right? So generally, a common thumb of rule that is used is there is very less probability by which the amplitude can be more than or less than the 4 sigma range. Because the area in the tail end of the curve is going to be very small. Now, depending on how strict the application is, meaning if you are doing some military application or an automobile application, wherein you can't afford to really have these outliers also, it could mean that a system is crashing, right? Then maybe instead of looking at 4 sigma, you might even look at 6 sigma or 7 sigma. Now that depends on the application you are working with. Okay. Now, if I were to look at a signal like this in frequency domain, would it make sense to calculate the Fourier series or Fourier transform? I mean, I have a signal. Anytime I think of the frequency domain, we immediately think of Fourier transform, right? So would it make sense to look at the Fourier transform of a signal like this?
Okay. What the Fourier transform of x?
Why? Right, but it's Fourier transform, right? Correct. So the problem with the Fourier transform is, let's say I observed it for 1 millisecond. I get some Fourier transform for it. Now, let's say I again observe it for another 1 millisecond. I'll get a very different Fourier transform. This Fourier transform itself is going to be time varying, right? So we can't use that to analyze the noise in the circuits. So instead of doing that, we look at its power spectral density. So this is in short PSD. This is also sometimes called as just the spectrum. Okay, so let me give you a thought process first. A thought experiment. Let's say I have this xn of t. Okay, I pass this through a bandpass filter. This bandpass filter has a bandwidth of 1 Hertz. And this is around some center frequency, FC. So I take the output of this bandpass filter and I connect this to some power meter. Okay. And then I can plot what is the measurement done by this power meter at a particular frequency, FC, right? So now I vary this FC from a minimum frequency, Fmin, to some maximum frequency, Fmax. And I repeat this experiment. So I get some curve like this. And this is called as the power spectral density of Xn of t. Okay. So basically, I'm looking at the average power in a 1 Hertz bandwidth around each frequency. Is this clear?
So now this will be having different strength of power spectrum density.
So no. So the signals that we generally deal with, the power spectral density remains a constant. So a very quick example you can think of is, let's say you have connected a mic, okay? You have some mic that is picking up noise from a large crowded room, right? So now, if I were to look at the output amplitude of the mic, that is going to be completely random, right? Now imagine I'm moving this mic closer to the crowd versus moving it away from the crowd. So if I move it closer to the crowd, it is going to pick up a lot more noise, right? That is, the intensity with which it is measuring this noise of the crowd is going to be much higher. If I were to look at its power spectral density, the value of the power is going to be much larger, right? Now I move it away, much away from the crowd. Then it is going to pick up the same signal, but with much lower intensity, right? So that is what we are capturing using this power spectral density. And for all the noises that we deal with, the power spectral density is not time varying. Now, there are signals where the power spectral density can also be time varying, but for the noises that we deal with, circuit noises, that is not the case. Okay, so I'm trying to give you an idea of what is meant by the power spectral density, right? So let's say you have a crowded classroom and people are allowed to randomly talk. There is no instructor in the class. If I keep a mic closer to the crowd, right in the middle of the crowd, it is going to pick up a lot of noise. The general chit chat. Chattering in the class, right? Now, if it is closer to the crowd, it is going to pick up a lot more chattering. Whereas if I move it backwards, it is still going to pick up the same signal, but with much lower intensity, much lower power, in other words, right? Similarly, so if you were in a river, in a forest closer to a river, you are hearing the same signal, but you are hearing it with much higher intensity if you are closer to the river versus if you're further away from the river, right? So this is the idea that we're trying to capture in this power spectral density.
Changing every time you measure it, there will be a different signal.
Correct.
So Fourier transform will be different.
Fourier transform is different, but it's the power in the signal at a given frequency remains the same. The time domain signal is varying, but the power of the signal for a given frequency doesn't vary with time.
For a large period of time, it will be more or less same. But if we look for a very narrow time period, then it will be changed.
So if you look for a, now as I'm changing this FC, the measurement I do So let's say this FC is a very small frequency value, okay, which means I need to observe for a larger period, right, to get the measurement corresponding to a small frequency. No, 1 hertz is the width of the band pass filter. FC is the center frequency. Correct. So you, correct. Sorry?
It won't always be the smaller frequency.
Right.
It's something similar to like the speed and velocity. Velocity can never be, it's always a speed. Need some time period. Like if we want to calculate Fourier transform, from first principle, we need to have signal for certain duration. We can't tell about for particular instant what is the application. Anything is like for PhD.
So let's take the example of FC being equal to 1 hertz.
That's why PSD comes from PDF, probability distribution. For that, more or less remains the same. We take it over a larger number.
So let me give you an alternate argument, right? Let's say I want to measure it for an FC of 1 hertz, right? That means I need to observe it for at least 1 second. So that I can, if I have to get properly measure something for 1 hertz, then I need to observe, I need to have a larger observation period of 1 second to actually fit in that signal. So other than that,
yeah, I mean, that captures the same thing.
Yeah.
Like, we are to do that in the frequency, the time duration needs to be very large.
the time duration needs to be very much. Yeah.
Medium to remain the more or less it and hence the PSD.
And then you can calculate the PSD. Okay. So the other comment I had for you is that the power spectral density, this for the signals that we are dealing with, power spectral density do not change with time. There are signals for which the PSD can also vary with time. But the noise signals that we deal with, PSD is a constant.
So,
Yeah.
so again, we want to calculate this noise power and CAD. So how can we do that?
So let me give you a detailed answer for that in the next class. Okay. But for now, let us look at the power spectral density of some of the common devices that you will deal with. So let's say I have a resistor. So if I take a resistor at any temperature other than 0 Kelvin, you will see that there are some random voltage fluctuations around this, right? So that is the thermal noise of the resistor. So its spectrum is given by some S of F. This is often represented as Vn square to show that this is actually a voltage quantity. And do you remember the value? So this is equal to 4 kTr. So where K is, it's a Boltzmann constant. What is the value? 1.38 into 10 to the power minus 23 joule per Kelvin. T is the temperature in Kelvin. What is the unit of this quantity? So basically, what is the unit of S of F? So it's, okay, watt per hertz. Okay, so this is assuming that you are calculating the exact power, right? In general, we represent it as volt square per hertz. So the resistor term is not there, basically. So it's V square per hertz. So in a lot of places, sometimes we represent the power of the signal as V square, right? So that given a resistor, you can easily calculate what the power is. Okay, so this is in volt square per hertz. So this is also in volt square per hertz. Okay, now this spectrum, if I plot in log scale, if I plot in any scale, will look like this, because it is now not a function of frequency. So this is a constant given by 4 kTr. This is also called as white noise. Why? Frequency independent. Okay, it's similar to how the white color has equal proportion of all visible light wavelengths. So similar to that, it has equal proportion of all frequency components. So now if I have a noisy resistor, I can represent this noisy resistor as an ideal resistor in series with the noise. Okay, where this Vn square is given by 4 kTr with units volt square per hertz. I can also represent this as a resistor with a current parallel to it. And this is some In square. What is the value? 4 kT by R unit ampere square per hertz. So now let's look at noise in a MOS transistor. There are two types of noise in a MOSFET. One is the thermal noise. And the other is the flicker noise. So thermal noise is modeled as a parallel current between its drain and a source. And its value is, do you know the value? 4 kT gamma GM, right? So you said 2 kT, right? Okay. So here K is Boltzmann constant, T is temperature, GM is transconductance, and gamma is a coefficient called as excess noise coefficient. This has a value equal to 2/3 for long channel transistors, and it approaches 1 for short channel transistors. So when you said 2 kT gamma GM, it actually reminded me of something. So this is a one-sided spectrum where I have shown only the positive frequencies. Now, in some cases, it is easier to deal with a two-sided spectrum where I have frequencies represented as both positive and negative numbers. So in that case, the spectrum will be at 2 kTr. Okay, so that the power of the signal remains the same. So this spectrum is again independent of frequency. There is no F in this expression. Therefore, I will have a flat spectrum like this. And hence, this is also called as white noise spectrum. The noise is modeled as a voltage source on the gate side. Vn square is given by it has low pass characteristics. Okay. So it's a constant K by WLCOX, and this is a function of frequency 1/f. So a lot of times you will represent this as S 1/f of f. Now this K is not Boltzmann constant, and this is called as, this is some process dependent coefficient. Now, because there is 1 by f here, it's actually easier to look at it in log scale. So if I plot the spectrum in log scale, this will look like this. Both of these are in log scale. Okay. So these are the three major types of noise sources that you will deal with, right? Flicker noise being low pass, as in why it is happening. Okay, so the exact reasoning I recommend you refer to devices textbooks, but qualitatively I can tell you this much. So at the interface between the silicon oxide and the channel, the electrons will get entrapped into.
There will be some dangling points, for which there will be some extra energy is. And from this energy shift and the economy jumping there, will be some slow frequency.
So electrons are getting trapped, and this is correlated. When they get released, is sort of correlated, which is why you have this shape, as far as I understand. Yeah, but for detailed explanation, you can refer to devices textbooks. Okay, so now another useful information that we need to know is this. Let's say I have a system, right? Some LTI system. This consists of resistors, capacitors, MOSFETs, etc. Right? And let's say there is some input node, and I have some noise at this input node. Okay, so this could be coming from a resistor or maybe from a MOSFET, doesn't matter for now, but I have some noise. I want to calculate how this noise is going to appear or propagate to the output. Okay, so how do I do this? I have to calculate the transfer function. Okay, so the first step is to calculate the transfer function. So you assume that this input noise source is a deterministic signal. Okay, then it becomes a regular linear system that you are familiar with a deterministic signal at the input, and you have an output, right? So you calculate the transfer function from input node to the output. Okay, assuming deterministic input signals. So this transfer function is also called as NTF, or noise transfer function. Okay, so once you have calculated this, so let's say this was equal to some h of s. Then the output noise is given by h of f the whole square into bn square n, where h of f is simply h of s, where s is equal to j 2 pi f. Okay, so now let me give you a problem to work on. Let's say this is some bias voltage, and this is my output node. Assume I naught is ideal, right? And this transistor has both thermal and flicker noise. Can you calculate what is the noise spectrum at the output? Please try. You can assume a transconductance of GM and an output resistance of RDS. So first, let me draw the small signal model. This is my V out, right? Now let me add the two noise sources. So I have some Vn square 1 by F here, and I have In square here. Okay. Next step would be to calculate the two transfer functions, H1 of S and H2 of S. Okay. So this is now a linear model. Therefore, to calculate these transfer functions, I'll rely on superposition and take one input at a time. So in calculating H1 of S, I have to de-energize the other input. So can you tell me H1 of S directly? Minus GM into RDS. Okay. For H2 of S, so the voltage here is going to result in a current flowing through this transistor that is given by GM into the input voltage. And this current has to now come out of this resistor, creating a voltage here. Therefore, the transfer function is minus GM into RDS. Now for H2 of S, I de-energize Vn. Because the gate to source voltage of this transistor is now 0, we cannot have a current flowing through this transistor. Therefore, the entire IN now has to flow through RDS. Therefore, H2 of S is equal to minus RDS. Right? So this is flowing in this direction. But as you'll see, the minus sign doesn't matter because you are going to take the square of it. So now let me directly write the output. Vn square out is going to be equal to H1 of F the whole square, which is GM RDS the whole square, into K by WL COX into 1 by F plus RDS the whole square, which is H2 of F the whole square, into 4 KT gamma GM. So I have to be taking magnitude of H2F the whole square because there is no frequency term involved. It's directly RDS square. Okay. Now I can plot the spectrum of Vn square out. What is the unit? Volt square per hertz in frequency. So I'm drawing both in log scale. So at very high frequencies, this term is going to be negligible and the spectrum will be dominated by the thermal noise. Now for very low frequencies, this will be dominated by the flicker noise. So you will have a plot looking like this. Right? Now I can extrapolate these constant straight lines. And they'll intersect at some point, right? So this frequency is called as the flicker noise corner, or sometimes just the corner frequency. And ideally, we would have liked this flicker noise corner to be as small as possible. Is this clear? So I know that there are some confusions related to taking the PSD, why PSD is valid, etc. So please think about this. If you have further questions on this, you can ask me in the next class. Okay, we can wrap up this class here. If you have any other questions on the midsum, you can ask me that as well.